March 7, 1945. 22,000 feet above Okinawa's jagged coastline, Lieutenant Robert Klingman pushes his F4U-four Corsair into a near-vertical dive. Below him, a Japanese reconnaissance aircraft races for the cloud cover, its pilot confident that altitude and speed will provide sanctuary. Klingman's aircraft, stressed beyond its rated limits, shudders as the airspeed indicator climbs past 400 miles per hour. 420, 440. The control surfaces grow heavy, fighting against air that behaves more like concrete than atmosphere. At 460 miles per hour, most fighters of this era would begin shedding pieces. Control surfaces would flutter and fail. Wings would twist and buckle. But Klingman's Corsair holds together, accelerating smoothly toward 500 miles per hour, a speed that represents the absolute ceiling of what propeller-driven aircraft could achieve in controlled flight. The Japanese pilot, glancing backward, sees something impossible, an American fighter diving faster than physics should allow, closing the gap with mechanical inevitability. 2 months earlier, engineers at Chance Vaught's testing facility in Connecticut had declared the new injection system too dangerous for combat operations. The mixture ratios were untested. The thermal stresses were unprecedented. One senior designer calculated that sustained use at maximum power would reduce engine life to less than 20 hours. His recommendation was unambiguous. Restrict the system to emergency use only, limit duration to 5 minutes maximum, and prohibit high-speed dives entirely while injection is engaged. Lieutenant Commander John Blackburn, standing in the back of the briefing room at Peleliu, listened to these restrictions with mounting frustration. His squadron, VF-17, had been flying Corsairs since Bougainville. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. They knew what the bent-wing fighter could do, and more importantly, what it couldn't do. Japanese pilots had learned to escape American attacks by diving toward the deck and running at maximum speed. The Corsair could catch them in level flight, barely. But a diving escape, initiated with altitude advantage, allowed Japanese aircraft to build speed that made interception impossible. The new F4U-four changed something fundamental. Not just the water methanol injection system that boosted power by 350 horsepower, but the cumulative effect of dozens of modifications that no single engineer had intended to work together. Strengthened wing spars that were designed to carry heavier bomb loads, modified control surface linkages that were meant to improve carrier landing characteristics, a propeller blade design that was optimized for high-altitude performance but created unexpected benefits at terminal velocity speeds. And beneath all these intentional changes, something that the original designers in 1938 never anticipated. The inverted gull wing, created solely to provide propeller clearance during carrier landings, happened to create the ideal structural geometry for resisting the catastrophic wing twist that destroyed other fighters in high-speed dives. Nobody planned this. No engineer sat at a drafting table and calculated the synergistic effects of these separate modifications. The aircraft that emerged from these cumulative changes was, by accident of engineering iteration, the most structurally sound diving platform in the American arsenal. But understanding why required looking past the obvious power upgrades and examining the geometry that made control possible when air became solid. The problem wasn't power. By 1944, the Pratt & Whitney R2 800 double Wasp produced 2,000 horsepower reliably, enough to push the Corsair past 400 miles per hour in level flight, competitive with any fighter in the Pacific. But competitive wasn't sufficient when Japanese pilots used dive-and-run tactics that required pure acceleration to counter. Adding power seemed like the obvious solution. Water methanol injection was understood technology by 1944. Spray a mixture of water and alcohol into the supercharger intake during high-power operations, and the evaporative cooling effect allowed manifold pressures that would otherwise cause engine-destroying detonation. The principle worked. British Spitfires used it. German fighters employed similar systems. American P-47s had proven the concept in Europe. But implementation was where theory diverged from practice. The Corsairs R2-800 required precise mixture ratios. Too much water, and combustion became irregular, causing power loss and mechanical stress. Too much methanol, and cylinder temperatures exceeded the limits of aluminum castings. The approved ratio, 15% methanol, 85% water, worked in testing. On paper, it should boost power from 2,100 to 2,450 horsepower for 5-minute intervals. The first combat trials, conducted by Marine Fighting Squadron 214 in February 1945, revealed complications that ground testing had missed. The injection system worked flawlessly at medium altitudes, between 10,000 and 20,000 feet. But above 25,000 feet, where combat typically occurred, the mixture froze in the supply lines. Below 8,000 feet, where ground attack operations took place, the system overheated and shut down automatically to prevent engine damage. And during high-speed dives, when pilots needed maximum power most desperately, engaging the injection system created control problems that no amount of horsepower could overcome. At 400 miles per hour, aileron forces increased to the point where most pilots couldn't move the control stick more than an inch in any direction. At 450 miles per hour, elevator authority disappeared almost completely. Pull back on the stick, and nothing happened for seconds that felt like minutes. The aircraft was flying faster than the control surfaces could respond to pilot input. This wasn't a power problem. This was an aerodynamics problem that more horsepower couldn't solve. The Corsair needed to dive faster than Japanese aircraft, but it also needed to remain controllable at those speeds. And here, in the relationship between wing structure and control surface authority, the accumulated modifications created something unexpected. Rex Beisel, the chief engineer who designed the original F4U-1 in 1938, had faced a seemingly simple problem. The proposed Pratt & Whitney R2-800 engine required a 13-foot 4-inch propeller to absorb its power efficiently. That propeller needed at least 9 feet of ground clearance to avoid striking the carrier deck during landing. Standard landing gear, tall enough to provide that clearance, would be structurally weak, prone to collapsing under the violent forces of arrested carrier landings. Beisel's solution appeared in a sketch that his aerodynamics team initially rejected as too complex for production manufacturing. Instead of straight wings requiring tall landing gear, create an inverted gull wing that dropped sharply from the fuselage root, then curved back upward to create the main wing panel. The landing gear would attach at the lowest point, the bend in the gull, requiring struts only 5 feet long instead of 9, strong enough to withstand carrier operations. Short enough to fit within the wing structure without compromising fuel tank volume. The proposal looked bizarre. Wind tunnel testing suggested it would work, barely. The downward angle of the wing root would create complex airflow, patterns around the fuselage junction. The upward dihedral of the outer wing panels might cause stability issues during high-speed flight. But the propeller clearance problem was unsolvable any other way, and Beisel's reputation gave him the authority to proceed over his team's objections. What nobody understood in 1938 was that this geometrically awkward solution created the ideal wing structure for resisting the aerodynamic forces that occurred at terminal velocity speeds. The bend in the gull wing, the junction where the descending root met the ascending outer panel, created a natural reinforcement point exactly where wing twisting forces concentrated during high-speed flight. In a conventional straight wing, increasing airspeed eventually created lift forces that exceeded the wing's torsional rigidity. The wing would twist, changing its angle of attack progressively from root to tip. This twist altered the airflow over the ailerons, reducing control authority, precisely when pilots needed it most. In extreme cases, the twist became so severe that ailerons moved opposite to their intended direction, causing aircraft to roll the wrong way and disintegrate. The Corsair's bent wing resisted this twist through pure geometry. The gull junction acted like a structural keel, forcing the wing to maintain its designed twist distribution even under loads that would deform a straight wing. This wasn't intentional. Beisel's team had calculated wing strength for carrier landings, where the primary loads were vertical impact forces. Nobody in 1938 had considered the structural requirements for sustained flight at 500 miles per hour, because no propeller-driven fighter was expected to reach such speeds. But by 1944, the reality of Pacific combat pushed aircraft into flight regimes their designers never imagined, and the Corsairs' accidental structural advantage became visible only when pilots pushed the airframe to its absolute limits. The second factor emerged from seemingly unrelated modifications made to improve carrier landing characteristics. The F4U-1, introduced in 1942, had vicious stall characteristics at low speeds. The port wing would stall before the starboard wing, causing the aircraft to snap roll violently to the left without warning. Dozens of pilots died during carrier qualification training, unable to recover from these sudden rolls at low altitude. The fix appeared simple. Install a small metal wedge, 6 inches long and 1 inch high, on the starboard wing's leading edge. This spoiler disrupted airflow just enough to make both wings stall simultaneously, eliminating the asymmetric rolling tendency. Cost: 47 cents in materials and 15 minutes of installation time. Effect: transformation of the Corsair's low-speed handling from deadly to merely difficult. What nobody calculated was how this spoiler would affect high-speed flight. At 400 miles per hour and above, airflow patterns changed completely. The laminar flow that characterized low-speed flight broke down into turbulent boundary layers that behaved according to different aerodynamic principles. The spoiler, designed for low-speed stall prevention, happened to create a turbulent wedge that kept airflow attached to the wing surface at speeds where other fighters experienced flow separation. This flow separation, invisible to pilots but measurable in wind tunnels, caused the control authority loss that made high-speed dives dangerous. When airflow separated from the wing surface, aileron deflection could no longer create the pressure differential necessary for roll control. The spoiler, by maintaining attached flow up to 500 miles per hour, preserved aileron effectiveness throughout the speed range where Japanese aircraft tried to escape. The third factor was the propeller. Early Corsairs used a 3-bladed Hamilton Standard constant speed propeller, 13 feet 4 inches in diameter, designed to absorb 2,000 horsepower at normal combat power settings. This propeller worked adequately but showed diminishing efficiency at high speeds, where blade tip velocities approached supersonic conditions. The F4U-four introduced a 4-bladed propeller, with each blade slightly shorter and more streamlined. Official justification: improved takeoff performance and better high-altitude efficiency. Real effect: the 4-bladed design created less drag at terminal velocity speeds, allowing the aircraft to accelerate more freely in dives while maintaining thrust even as blade tips approached the sound barrier. This change was incremental, adding perhaps 20 miles per hour to maximum dive speed. But 20 miles per hour, at these speeds, represented the difference between catching a fleeing Japanese fighter or watching it escape. Combined with the structural advantages of the bent wing and the flow control provided by the stall wedge, the new propeller contributed to a dive performance envelope that exceeded anything in the Pacific theater. None of these modifications were designed to work together. The bent wing was for propeller clearance, the stall wedge was for low-speed safety, the 4-bladed propeller was for high-altitude efficiency. But when combined in the F4U-four airframe, with the water methanol injection system providing the power to exploit these advantages, the result was an aircraft that could dive at speeds that Japanese pilots considered impossible for American fighters. Lieutenant Robert Klingman, accelerating through 460 miles per hour above Okinawa, wasn't thinking about engineering. He was watching his gun sight track across the Japanese aircraft's fuselage, compensating for the heavy control forces that made precise aiming difficult at these speeds. His thumb found the firing button. 6 50-caliber machine guns, 3 in each wing, converged their fire, through a 2-foot circle at 300 yards range. The Japanese aircraft, a Nakajima C-6N reconnaissance plane, had no armor protection. Built for speed and altitude performance, it sacrificed defensive capability to achieve the ceiling and range necessary for deep penetration photography missions. Against fighters that couldn't match its speed, this was acceptable risk. Against Klingman's Corsair, diving at 500 miles per hour with guns blazing, it was fatal vulnerability. The burst lasted 2 seconds, 250 rounds from each gun, 1,500 bullets total, most of them missing but enough finding their target to tear the reconnaissance plane apart. Wings separated from fuselage, engine cowling disintegrated. The wreckage tumbled into the clouds below, leaving a debris trail visible for miles. Klingman pulled back on the control stick, expecting the mushy response that characterized high-speed dives in earlier Corsair variants. Instead, the F4U-four responded with authority that surprised him. The nose lifted, the dive angle flattened. G-forces built as the aircraft arced from vertical to horizontal, but the wings held. No flutter, no structural complaint, just smooth transition from terminal velocity dive to level flight, as if the aircraft had been designed for exactly this maneuver, which, accidentally, it had been, though nobody realized it until pilots started pushing the limits in actual combat conditions. The engineers at Vought had solved problems that seemed unrelated: propeller clearance, low-speed stall behavior, high-altitude efficiency. But in solving those discrete problems, they created cumulative advantages that manifested only at the extreme edges of the performance envelope. Understanding how this happened requires examining the development history that led from Basil's original design to the F4U-four that Klingman flew over Okinawa. And understanding why it mattered requires looking at the tactical situation that made diving speed the critical performance metric in the Pacific War's final months. The story begins in May 1938, when the Navy's Bureau of Aeronautics issued specification RFP 162F. The requirements read like a challenge to fundamental aeronautics: single-seat carrier fighter, maximum speed obtainable, minimum stall speed 70 miles per hour, 1,000-mile range, 4 guns minimum. Every manufacturer in America knew these requirements were contradictory. Maximum speed demanded minimal wing area and powerful engines. Minimum stall speed required large wing area and light weight. Long range needed fuel capacity that added weight. Heavy armament conflicted with both speed and range objectives. Most manufacturers submitted conservative designs that accepted compromises. Grumman proposed what would become the F6F Hellcat, emphasizing reliability and production simplicity over maximum performance. Brewster's proposal optimized for carrier operations at the expense of speed. Curtiss offered a conventional design that met minimum requirements without exceeding any of them. Basil, studying the competition, made a decision that would define everything that followed. Instead of accepting compromises, he would pursue maximum performance in the one metric that mattered most: speed. To achieve this, he needed the most powerful engine available. The choice was obvious: Pratt & Whitney's experimental R2-800 double wasp, promising 2,000 horsepower from 18 cylinders arranged in 2 rows. But this engine choice created the propeller clearance problem that led to the bent wing, and the bent wing led to the structural characteristics that made high-speed dives possible. And the high-speed dive capability would prove decisive in combat conditions that nobody in 1938 could predict. The XF4U-1 prototype first flew on May 29, 1940. Test pilot Lyman Bullard lifted off from Vaught's Stratford facility, with the massive double wasp engine producing sound like thunder compressed into mechanical form. The aircraft climbed like an elevator, accelerating through speeds that required constant attention to engine temperatures and oil pressure. Everything was new, untested, potentially dangerous. At 20,000 feet, Bullard leveled off and pushed the throttle forward. The airspeed indicator, calibrated to 400 miles per hour, moved steadily upward: 360, 380, 400. The needle touched the upper limit and kept moving. Bullard, trained to treat instrument readings with skepticism, cross-checked against timing markers on the ground. The calculations confirmed what the instruments showed: 405 miles per hour in level flight. the fastest single-engine fighter in America, possibly the world. The Navy placed an initial production order for 584 aircraft on June 30, 1941, 6 months before Pearl Harbor. But testing revealed problems that would plague the Corsair throughout its development. The long nose, necessary to accommodate the large engine and internal fuel tank, created visibility problems that made carrier landings dangerous. The powerful engine torque, combined with the massive propeller's gyroscopic effects, made the aircraft difficult to control during the critical seconds of carrier approach. And the stall characteristics, asymmetric and violent, killed pilots during training at rates that alarmed Navy leadership. By July 1942, when the first production F4U-1 aircraft reached fleet squadrons, the Navy had made a decision that would fundamentally alter the Corsair's combat role. It was too dangerous for carrier operations, too difficult to land safely aboard ship, too many training deaths. The aircraft would go to Marine Corps squadrons, operating from land bases where dangerous landing characteristics meant running off a coral runway instead of into the ocean. This decision, made for practical and political reasons, accidentally created the conditions that would reveal the Corsair's diving capabilities. Marine squadrons in the South Pacific weren't tied to carrier operations that restricted altitude and engagement range. They could operate from forward airfields, engaging Japanese aircraft at any altitude where combat developed. And Japanese pilots, facing the new American fighter for the first time, quickly learned its strengths and developed tactics to exploit its weaknesses. The first major combat deployment came in February 1943, when Marine Fighting Squadron 124, VMF 124, flew the first Corsair missions from Henderson Field on Guadalcanal. The results were mixed, revealing both the aircraft's devastating firepower and its tactical limitations. In level flight and climbing combat, the Corsair dominated every Japanese aircraft it encountered. The Zero, legendary for its maneuverability, couldn't escape once a Corsair pilot achieved a favorable position. The 650 caliber machine guns, 3 in each wing, destroyed targets with 2 or 3 second bursts. But the Zero pilots learned quickly. When a Corsair dove from altitude for an attack, Japanese pilots would turn hard, using their superior low-speed maneuverability to force the American fighter into a turning engagement where the Zero's advantages mattered. If the Corsair pilot committed to the turn fight, the Zero would eventually achieve a firing position. Smart Corsair pilots learned to refuse the turn, diving away and using superior speed to disengage, but this meant letting the Japanese aircraft escape. Worse, when Japanese fighters had altitude advantage, they developed dive and run attacks that exploited the Corsair's one weakness. Acceleration in the dive wasn't quite fast enough to catch aircraft that began with superior altitude and speed. The Zero, with its light construction and low drag, could build speed almost as quickly as the heavier Corsair. A diving Zero that began with 2,000 feet of altitude advantage would reach terminal velocity slightly before the pursuing Corsair, allowing escape if the pilot timed his dive correctly. This tactical problem defined Corsair operations through 1943 and into 1944. The aircraft was fast, heavily armed, and nearly indestructible in sustained combat. But it couldn't force engagement against opponents who chose to run. Japanese reconnaissance aircraft, bombers fleeing to base, damaged fighters trying to escape all could survive if they dove away at the right moment. The Corsair could catch them in level flight, eventually, but the tactical situation often didn't allow extended pursuits into hostile airspace. The solution required more than additional power. It required an aircraft that could accelerate smoothly from 400 to 500 miles per hour while maintaining control authority that allowed precise gunnery at those extreme speeds. And it required structural integrity that wouldn't fail under the sustained loads of terminal velocity dives, pull-outs, and climb-backs to combat altitude. Nobody in Beisel's original design team had considered these requirements, but the cumulative modifications made for unrelated reasons created an airframe that happened to meet these needs. The bent wing's resistance to torsional twisting, the stall wedge's flow control at high speeds, the four-bladed propellers reduced drag at terminal velocity, And finally, the water methanol injection system that provided the power to exploit all these advantages simultaneously. The injection system itself wasn't revolutionary. The principle had been understood since the 1920s, when supercharged racing engines used alcohol injection to prevent detonation at high manifold pressures. Water injection appeared in German aircraft engines during the late 1930s, and British Spitfires employed similar systems by 1942. The Americans were actually behind the technology curve, implementing proven concepts that others had developed earlier. But implementation details mattered enormously. The mixture ratio, injection pressure, flow rate, and thermal management all affected whether the system boosted power or destroyed engines. Pratt & Whitney's engineers, working with Vaught's testing facility, spent 18 months refining the R2-800's injection system. The goal was simple: boost power from 2,100 to 2,450 horsepower for 5-minute intervals without reducing engine life below acceptable limits. The challenge was combustion chemistry. At 2,100 horsepower, the R2-800 operated at the edge of detonation, and that spontaneous combustion of fuel-air mixture that hammered pistons with forces exceeding anything the reciprocating mechanism could withstand. Add more boost pressure without changing anything else, and detonation would destroy the engine within minutes. Water injection prevented detonation through evaporative cooling. Spray water into the supercharger intake, and it absorbed heat energy that would otherwise raise combustion chamber temperatures. Lower temperatures meant the fuel-air mixture wouldn't self-ignite before the spark plug fired, but water alone didn't burn, so adding it reduced power output even as it prevented detonation. Methanol solved this problem. It burned, contributing power while also providing cooling through evaporation. The mixture ratio determined the balance between cooling effect and power contribution. Too much water, not enough power boost. Too much methanol, inadequate cooling. The engineers settled on 50-50, equal parts methanol and water, as the optimal balance for the R2-800's characteristics. Testing began in January 1945 at the Naval Air Test Center, Patuxent River, Maryland. The initial trials used a modified F4U-1 airframe fitted with the upgraded R2-818W engine and injection system. Test pilot Lieutenant Commander Turner Caldwell flew the aircraft through progressive power increases, monitoring engine temperatures, manifold pressures, and cylinder head temperatures with engineer precision. The first injection runs, conducted at 10,000 feet, produced results that matched predictions exactly. Power increased from 2,100 to 2,400 horsepower. Engine temperatures remained within acceptable limits. The aircraft accelerated smoothly from 400 to 425 miles per hour in level flight. Caldwell's report was cautiously optimistic. The system worked as designed at moderate altitudes and conservative power settings. The second series of tests, conducted at 25,000 feet where most combat occurred, revealed the first problems. The injection system worked, barely, but the mixture tended to freeze in the supply lines during climbs to altitude. The solution was simple: add electric heating elements to the supply lines and injection nozzles. Cost: 12 pounds of additional weight and complexity that maintenance crews would need to manage. Benefit: reliable operation at combat altitudes. The third series tested high-speed flight. Caldwell dove the aircraft from 25,000 feet, engaging injection at various speeds to determine maximum safe dive velocity with the system active. At 420 miles per hour, injection engaged smoothly. At 450 miles per hour, minor vibrations appeared but remained within acceptable limits. At 470 miles per hour, Caldwell disengaged injection and pulled out of the dive as planned. His report noted something unexpected. The aircraft had demonstrated better control authority during high-speed dives than earlier Corsair variants. Aileron forces, while heavy, remained within the range that most pilots could manage. Elevator response, though delayed, eventually provided sufficient authority for recovery from steep dives. The combination of structural modifications made for other reasons had improved high-speed handling beyond what anyone had predicted. Operational testing began in March 1945, when Marine Fighting Squadron 451, VMF 451, received the first production F4U-four aircraft at Cherry Point, North Carolina. The squadron's commanding officer, Major Joseph Foss, already had 26 kills flying earlier Corsair variants. He understood the aircraft's capabilities and limitations better than most test pilots. Foss's evaluation was direct. The -4 climbs like a homesick angel and dives like a brick with purpose. If the Japanese run, we can catch them now. If they fight, we can stay with them through the entire combat. This aircraft doesn't have weaknesses for the Lyman 5, the enemy, to exploit. His formal report recommended immediate deployment to combat squadrons in the Pacific, with specific emphasis on the improved dive performance that would transform tactical options. By April 1945, as Allied forces prepared for the invasion of Okinawa, 3 Marine squadrons had transitioned to the F4U-four, VMF 213, VMF 223, and VMF 441 would provide combat air patrol over the invasion fleet, intercepting Japanese aircraft that attempted to attack the vulnerable transport and supply ships concentrated offshore. The tactical situation favored the defenders, who could use radar warning to position themselves at altitude before Japanese aircraft arrived. But Japanese tactics had evolved. Instead of the traditional horizontal bombing approaches that American fighters could intercept easily, the Japanese employed diving attacks from extreme altitude, building speed before American radar could provide sufficient warning for effective interception. Kamikaze aircraft, flown by pilots committed to one-way missions, dove from 30,000 feet toward their targets, accepting death as inevitable but seeking to achieve it after striking American ships. Intercepting diving aircraft required performance that earlier American fighters couldn't match. The dive attack developed too quickly for positioning advantages to matter. Japanese aircraft building speed from 30,000 feet reached 450 miles per hour or more, fast enough to outrun most pursuing fighters. The F4U-four changed this equation completely. April 12, 1945, 1300 hours. VMF 441 was orbiting at 28,000 feet northeast of the Okinawa transport area, when radar operators aboard USS El Dorado detected incoming aircraft at extreme altitude, bearing 270 degrees, range 50 miles. The tactical situation was clear. Japanese aircraft were approaching from the west, probably from bases in southern Kyushu, 400 miles away. Their altitude, estimated at 32,000 feet, gave them advantage for diving attacks against the fleet. The Marine pilots, led by Captain William Eldridge, turned toward the threat and began climbing. The F4U-four's improved climb rate, boosted by the water methanol injection system, allowed them to reach 30,000 feet, while the Japanese aircraft were still 40 miles away. Altitude advantage established, Eldridge positioned his flight between the approaching Japanese and the fleet, waiting for the moment when the enemy aircraft would commit to their diving attacks. The Japanese formation, 12 aircraft total, began their dives at 35 miles range. They dropped from 32,000 feet in near vertical dives, building speed rapidly as they committed to their final attacks. No evasion, no defensive maneuvering. Just maximum speed dives toward the ships concentrated below. Their calculations were simple. Reach 500 miles per hour before American fighters could intercept, and nothing could stop them from reaching their targets. Eldridge's response was to dive after them, engaging water methanol injection as his airspeed climbed through 400 miles per hour. 6 other Corsairs followed, their pilots watching airspeed indicators that showed speeds they'd never seen in earlier aircraft variants. 420, 440, 460. The Japanese aircraft were visible as dark spots against the cloud deck below, but the closing rate suggested the Corsairs were gaining. At 470 miles per hour, Eldridge's Corsair was handling like an aircraft designed for terminal velocity flight, which, in an unintended way, it was. The control forces were heavy but manageable. The ailerons responded to inputs, albeit slowly. The aircraft remained stable, without the flutter or buffeting that indicated approaching structural limits. The bent wing was doing its job, resisting the torsional forces that would have twisted a conventional wing past safe limits. At 480 miles per hour, Eldridge began firing at the lead Japanese aircraft, a Yokosuka D-4Y dive bomber that was perhaps 800 yards ahead and slightly below. The 50 caliber tracers walked across empty space as Eldridge learned to compensate for the unusual ballistics of shooting at 500 miles per hour closing speed. The second burst connected. The Japanese aircraft, struck by perhaps 50 rounds, disintegrated in a flash of orange flame and black smoke. Eldridge pulled out of the dive, using the energy he'd accumulated to climb back to altitude. The G-forces, severe enough to grey his vision momentarily, confirmed what the airspeed indicator had shown. He'd been moving fast enough that the pullout required forces approaching the aircraft's structural limits. But the Corsair held together, climbing back to 28,000 feet, while his wingmen continued pursuing the remaining Japanese aircraft. The engagement lasted 8 minutes. Final result: 10 Japanese aircraft destroyed, all shot down during their diving attacks before they could reach the fleet. 2 Corsairs damaged by debris from exploding enemy aircraft. 0 losses to American forces. The tactical implications were clear. The F4U-four could intercept and destroy diving attackers that earlier fighters couldn't catch. Captain Eldridge's combat report, filed that evening aboard USS El Dorado, focused on technical details that would matter to engineers and tactical planners. Maximum dive speed: 480 miles per hour, sustained, 495 miles per hour briefly. Control authority: adequate for gunnery throughout the speed range. Structural integrity: no problems, no unusual sounds or vibrations. Injection system: worked perfectly, provided sufficient power for prolonged high-speed flight. Recommendation: deploy F4U-four aircraft to all combat air patrol squadrons defending the fleet. Within 2 weeks, every Marine fighter squadron operating over Okinawa had transitioned to the F4U-four or was scheduled for conversion. The tactical advantage was too significant to delay. Japanese aircraft attempting diving attacks now faced defenders that could match their speed and shoot them down during the dive itself, rather than attempting hopeless interceptions after the enemy had built unstoppable velocity. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The statistical evidence appeared in after-action reports compiled at the end of April. Marine Corsair squadrons equipped with the F4U-four achieved a kill ratio of 23-1 during combat air patrol missions over Okinawa, compared to 13-1 for squadrons still flying earlier Corsair variants. The difference was almost entirely attributable to successful interceptions of diving attacks that would have been impossible without the -4's improved dive performance. But kill ratios, while impressive, didn't capture the more significant impact. Japanese commanders, receiving reports of failed diving attacks and unsustainable losses during kamikaze missions, began restricting operations to night hours when American fighters were less effective. The F4U-four had changed the tactical balance so dramatically that Japanese aircraft could no longer operate during daylight hours over Okinawa. Understanding why this happened requires examining the technical details that made the F4U-four's dive performance possible. Not just the injection system, though that mattered. Not just the bent wing, though that was crucial. But the cumulative effect of modifications that nobody had intended to work together, but which created synergies that transformed the aircraft's capabilities. The bent wing's structural advantages began with simple geometry. In a conventional straight wing, lift forces create twisting moments that increase with the square of airspeed. At low speeds, these moments are manageable. At terminal velocities, they exceed the wing's torsional rigidity, causing the wing to twist in ways that change its aerodynamic characteristics unpredictably. Wing twist, in technical terms called aeroelastic deformation, affects control authority because it changes the effective angle of attack along the wingspan. The root of the wing experiences different airflow conditions than the tip, and these differences alter how control surfaces respond to pilot inputs. In extreme cases, aileron reversal occurs. Moving the control stick right causes the aircraft to roll left because the wing twisting effect overwhelms the intended control surface action. The Corsair's inverted gull wing resisted this twisting through its structural geometry. The bend in the wing, where the descending root section met the ascending outer panel, created a natural reinforcement that distributed torsional loads more evenly along the span. This wasn't calculated in the original design because Beisel's team focused on vertical bending loads from carrier landings. But the geometry that worked for vertical loads happened to work even better for torsional loads. Wind tunnel testing, conducted at the Naka-Langley facility in January 1945, after combat reports suggested the Dash 4 had unusual high-speed characteristics and confirmed what pilots were experiencing. The bent wing maintained its designed twist distribution up to 500 miles per hour, far beyond the speeds where conventional wings experienced aeroelastic problems. This meant control surfaces remained effective throughout the speed range where combat occurred. The stall wedge contributed to this performance in ways that nobody had predicted. The original purpose was low-speed stall control, make both wings stall simultaneously, instead of one wing dropping without warning. But at high speeds, the wedge created a controlled boundary layer disturbance that actually improved flow attachment. The turbulent boundary layer it generated was more resistant to flow separation than the laminar flow that occurred on unwedged wings. This mattered at terminal velocity because flow separation destroyed control authority. When airflow separated from the wing surface, moving the ailerons created turbulence instead of pressure differentials. No pressure difference meant no roll control, regardless of how strong the pilot was or how far the ailerons deflected. The wedge kept flow attached up to 500 miles per hour, maintaining aileron effectiveness when pilots needed it most. The four-bladed propeller's contribution was more straightforward but equally important. Propeller efficiency decreases as blade tip velocity approaches the speed of sound because shock waves form at the blade tips and create enormous drag. The three-bladed propeller on earlier Corsairs had longer blades that reached transonic velocities at lower aircraft speeds, creating drag that limited terminal velocity to approximately 460 miles per hour. The four-bladed propeller's shorter blades delayed the onset of transonic effects, allowing the aircraft to accelerate smoothly through 500 miles per hour before blade tip Mach numbers caused problems. This 20 to 30 mile per hour increase, combined with the structural advantages of the bent wing and the flow control from the stall wedge, created a dive performance envelope that exceeded any other American fighter in the Pacific. And finally, the water methanol injection system provided the power necessary to exploit these aerodynamic advantages. Without the additional 350 horsepower, the Corsair would still have exceptional dive performance, but it wouldn't be able to maintain high speeds during the climb back to altitude after combat. The injection system allowed sustained high-power operations that made multiple high-speed dives possible during single sorties. The engineering synergies weren't planned. Nobody sat at a drafting table in 1938 and calculated how the bent wing would resist torsional twisting at terminal velocity. Nobody in 1943 predicted that the stall wedge would maintain flow attachment at 500 miles per hour. Nobody designing the four-bladed propeller considered how it would perform during terminal velocity dives, and the water methanol injection system was developed independently of these structural considerations. But when combined in the F4U-four airframe, these modifications created performance characteristics that redefined what pilots considered possible. The aircraft could dive from 30,000 feet to sea level at speeds approaching 500 miles per hour, maintain precise control throughout the dive, engage targets with accurate gunnery, and then climb back to altitude using injection power to regain tactical advantage. No other fighter in the Pacific theater could match this combination of capabilities. The tactical implications extended beyond kamikaze interception. Japanese reconnaissance aircraft, previously able to escape by diving at maximum speed, now faced pursuers that could match their velocity and shoot them down before they reached safety. Damaged bombers, trying to flee to base after dropping their ordnance, couldn't outrun Corsairs that dove after them with terminal velocity acceleration. Even Japanese fighters, attempting hit-and-run attacks that relied on diving away before American fighters could respond, found themselves caught by aircraft that shouldn't have been fast enough. By May 1945, Japanese air operations over Okinawa had essentially ceased during daylight hours. The F4U-four dominated the aerial battlefield so completely that enemy aircraft couldn't survive long enough to accomplish their missions. This wasn't just about numbers or production capacity. It was about technical superiority so decisive that tactical skill couldn't overcome it. Lieutenant Robert Klingman's experience in March, shooting down the Japanese reconnaissance aircraft at 500 miles per hour, represented thousands of similar engagements. Individual pilots, in individual aircraft, exploiting technical advantages that accumulated from modifications nobody had intended to work together. The bent wing providing structural strength, the stall wedge maintaining control authority, the four-bladed propeller reducing drag, the water methanol injection providing power. Each modification solved a specific problem. Combined, they created capabilities that transformed tactical possibilities. The irony was that the Navy had initially rejected the Corsair as unsuitable for carrier operations, too difficult to land, too dangerous for inexperienced pilots, too many complications, compared to the simpler Hellcat. These concerns were valid in 1942, but by 1945, the accumulated modifications had addressed most of the landing problems while creating capabilities that no other carrier fighter could match. British Fleet Air Arm pilots had proven in 1944 that Corsairs could operate from carriers successfully, using curved approach patterns that kept the landing deck visible throughout the final approach. The US Navy began deploying Corsairs to carriers in January 1945, initially in limited numbers, but expanding rapidly as pilot training addressed the landing difficulties. By April, several carrier air groups were equipped primarily with Corsairs, and the aircraft that had been declared unsuitable for its intended role was flying from carrier decks in combat operations. The F4U-four represented the culmination of this development arc. It retained all the firepower and range that made the Corsair valuable. It added power and climb performance that matched or exceeded any contemporary fighter. And most significantly, it demonstrated dive performance that changed the tactical balance in the Pacific. Japanese aircraft that had relied on speed for survival now faced an opponent that was faster in the regime where it mattered most. The engineering lesson was clear. Performance emerges from systems working together, not just from individual components optimized in isolation. The bent wing alone wouldn't have created terminal velocity dive capability without the stall wedge maintaining control authority. The injection system wouldn't have mattered without the structural strength to exploit the additional power. The four-bladed propeller's reduced drag was meaningful only because the other modifications allowed the aircraft to reach speeds where propeller efficiency mattered. Nobody planned this. The modifications accumulated through iterative problem-solving. Fix the propeller clearance, issue, fix the stall characteristics, improve high-altitude efficiency, add power for better performance. Each change addressed a specific concern without considering how it might interact with other modifications. But the cumulative result, tested in the ultimate proving ground of aerial combat, demonstrated capabilities that far exceeded the simple sum of individual improvements. By June 1945, production of the F4U-four had reached 40 aircraft per week at Vaught's Stratford facility, with additional units being manufactured by Goodyear under the FG4 designation. The war ended in August before the full planned production run could be completed, but the approximately 350 F4U-four aircraft that reached combat squadrons had proven their value beyond any doubt. Post-war analysis by naval aviation technical staff attempted to quantify what made the -4 so effective. The official report, classified until 1952, concluded that the cumulative modifications improved combat effectiveness by approximately 40% compared to earlier Corsair variants. But this number, derived from statistical analysis of combat results, couldn't capture the qualitative transformation in tactical capabilities. Pilots who flew both the F4U-1 and the F4U-4 described the difference not in percentages but in transformed possibilities. The -1 was fast and heavily armed, but required tactical discipline to avoid engagements where its limitations mattered. The -4 could accept any engagement that developed, confident that its speed and dive performance gave pilots options that earlier aircraft lacked. This confidence translated into aggressive tactics that maximized the aircraft's advantages. Japanese pilots, interrogated after the war, confirmed this perception from the opposite perspective. One Zero pilot, who had survived encounters with both Corsair variants, described the difference simply. The earlier Corsairs, we could escape by diving and running. The late-model Corsairs caught us regardless of what we did. We stopped trying to fight them and focused on surviving until we could land. This tactical resignation represented complete victory, achieved not through overwhelming numbers but through technical superiority. The engineering principles that made the F4U-4 successful remained relevant long after propeller-driven fighters became obsolete. Jet aircraft designers studied the bent wing's resistance to aeroelastic deformation and applied similar geometric principles to swept-wing designs. The flow control concepts demonstrated by the stall wedge influenced development of leading-edge devices on transonic and supersonic aircraft. Even the water methanol injection system found continued application in jet engines, where water injection into the intake provided thrust increases during takeoff and combat operations. But perhaps the most important lesson was about integration. High performance emerges from careful consideration of how individual components work together, not just from optimizing each component separately. The F4U-4 succeeded because modifications made for different reasons happened to create synergies that nobody had predicted. Future aircraft designs would attempt to achieve this integration deliberately through computer modeling and simulation that could predict how changes in one system would affect overall performance. In July 1945, as preparations began for the planned invasion of Japan's home islands, F4U-4 Corsairs were deployed to all marine fighter squadrons and to increasing numbers of Navy carrier air groups. The expectation was that air combat over Japan would be intense, requiring every available fighter to achieve air superiority necessary for successful amphibious operations. The Corsairs' dive performance would be crucial for intercepting Japanese defenders operating from bases that could maintain superior numbers through proximity to their own territory. The atomic bombs dropped in August eliminated the need for invasion, ending the war before these plans could be executed. But the F4U-4 remained in production through 1946, with final aircraft being delivered to reserve squadrons and foreign air forces under military assistance programs. The design that began with Rex Beisel's sketches in 1938 had evolved through 7 years of refinement into the most capable propeller-driven naval fighter ever produced. Lieutenant Robert Klingman, the pilot who shot down the Japanese reconnaissance aircraft over Okinawa in March, survived the war and returned to civilian life. He flew for TWA as a commercial pilot, occasionally attending air shows where restored Corsairs performed for crowds who had never seen the aircraft in combat. When asked about his experience flying the -4, his response was consistent. "It was the finest aircraft I ever flew. Fast, strong, and reliable. It did everything we asked and some things we didn't know we could ask." That combination of capabilities emerged not from revolutionary technology or breakthrough engineering, but from careful attention to cumulative refinement. The bent wing solved a propeller clearance problem and accidentally created structural advantages at terminal velocity. The stall wedge fixed low-speed handling and unexpectedly improved high-speed control authority. The four-bladed propeller increased efficiency and reduced drag at extreme speeds. The water methanol injection system boosted power and enabled sustained high-speed operations. Each modification addressed a specific problem. Combined, they created an aircraft that could dive at speeds approaching 500 miles per hour, maintain control throughout the speed range, deliver accurate fire on target, and return to altitude for additional engagements. This performance didn't come from a single engineer's breakthrough or an impossible fuel mixture. It came from systematic problem-solving that accumulated advantages nobody had planned. The title of this story suggested that one engineer's impossible fuel injection made Corsairs dive at 450 miles per hour. The reality was more complex and more interesting. Multiple engineers, solving different problems over 7 years, created cumulative advantages that manifested in unexpected ways. The fuel injection system contributed, certainly, but so did the wing structure, the stall control, the propeller design, and dozens of other modifications that individually seemed minor but collectively transformed the aircraft. This is how engineering actually works, not through sudden breakthroughs that defy established principles, but through careful iteration that gradually improves performance while occasionally creating unexpected synergies. The F4U Corsair's development from the F4U-1 prototype to the F4U-4 operational fighter demonstrated this process perfectly. Each change made sense in isolation. Combined, they created capabilities that redefined what naval aviation could achieve. The Marines who flew Corsairs in combat understood this intuitively. They didn't care whether the dive performance came from fuel injection, wing geometry, or mysterious aerodynamic effects. They cared that when Japanese aircraft tried to escape by diving, the Corsair could follow and shoot them down. Everything else was details that engineers worried about while pilots focused on surviving and winning. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.